All right, so this is going to be a crash course in doing a one sample t-test. And so in this tutorial, I will review null hypothesis significance testing in general, because a one sample t-test is an example of doing a null hypothesis significance test. So one sample t-test is also called a single sample t-test. So types of research questions that we can answer with a one sample t-test would be, does winning the lottery increase happiness? Does a therapy reduce depression? Does a new antipsychotic drug reduce hallucinations? Does the amount of time spent on social media affect stress? Critically, with these questions, the research methodology for a one sample t-test involves collecting just a single sample of participants and then comparing the mean of that sample to a known population mean, which is called mu. Okay, so that's this Greek symbol that looks like a squiggly U. It's a Greek letter mu, and that's used to designate a population mean. So in order to do a one sample t-test, you have to have some information about a population of interest. So let's just say with this example, does winning the lottery increase happiness? You would need to know or be able to make a reasonable assumption about the average happiness score in the population. And so for many psychological variables, this information exists. So happiness is something that is studied extensively, usually with fairly standard instruments. And so because there's been large scale studies, that would be an example of something where we could say that we do have a known population mean, and we could take a sample of people, like a sample of lottery winners, and we would be able to compare that sample of lottery winners to that known population average. And so the rest of these questions would kind of operate in the same way, but we'd need to have that population mean. We don't necessarily need to know any other characteristics of our population. So in particular, we don't know what the variability in the population is. We don't know what the variance in standard deviation is, but we will estimate that from our sample data. And so that's the difference between doing a one sample t-test versus a z-test. But a one sample t-test is a type of null hypothesis significance test, and so I want to review null hypothesis significance testing very, very briefly. So null hypothesis significance testing, you start with the assumption that the study that you're doing doesn't work, or the effect that we believe is true is not actually true. And so we formalize this belief as the null hypothesis. So for example, our starting place would be that the therapy does not reduce depression, or that winning the lottery does not increase happiness. It would actually take just a little while to do a proper explanation of why statistical significance tests are set up this way. But kind of the short of it is, it's a lot easier to refute something or disconfirm something than it is to provide confirming evidence. So many years ago, statisticians came up with this idea, and they said, you know what, let's do our tests by setting up a null hypothesis, and then we'll provide evidence that the null is wrong, and that will be an indirect way to provide evidence for, say, a research hypothesis. So it's a very backwards way of proceeding, but that's how it works. So anytime you read a research report or you hear some statement in the popular press or the media about a study had statistically significant results, they're still referring to this null hypothesis significance testing process. Okay, so here's just a little bit more about how it works. But again, our starting place is the null meaning no effect, and we start with an assumption that our study doesn't work. And then what we're actually going to do is say, well, okay, if the null is true, what is the likelihood of actually getting the result that we did? So we start from the premise that our study doesn't work, and then we can evaluate the probability of getting the results that we did relative to the assumption that it doesn't work. Again, very weird, but this is how it works. Right, so ultimately statistical significance is a judgment about the likelihood of the results of a study being due to randomness or pure chance, assuming that the null hypothesis is true. So as in, okay, if we start with the null and winning the lottery does not actually increase happiness, what are the chances of getting a sample mean with the value that we obtained in our study? And so if we say to ourselves, well, if our starting place is that winning the lottery doesn't increase happiness, and now we take a sample of lottery winners and they seem to have a sample mean that seems very, very high, so high that it just seems not probabilistic. It seems improbable that we would get a sample mean this large if our first assumption is that the lottery does not actually increase happiness. Okay, and basically, if the likelihood is low, more specifically, if the probability is less than 5%, that we would get a sample mean that is either so large or so small based on what we expect ahead of time, if the null is true, that is no effect of what we're doing, then it's then when we say that we have a statistically significant result. Okay? So a statistically significant result is a result that happens less than 5% of the time if we assume that the null hypothesis is true and our study has no effect. Quite strange, but it's true. That's the way it works. All right. Now, a little bit more detail about how that actually works is because you might be thinking to yourself, well, how could you ever know that? Here's how we know that. What you have to do is you have to create a sampling distribution. A sampling distribution or sampling distributions are theoretical. They're theoretical distributions that are used to estimate the probability of obtaining a sample statistic. So with a one-sample t-test, our sampling distribution that we use is called a sampling distribution of the mean, or the sampling distribution of the sample mean. So when you've taken your stats class, I'm sure you learned all about that, or if you haven't, you will. What we rely on is something called the central limit theorem. So mathematicians came up with this, and in my classes, we don't go real deep into it because it's not really a math class, it's a psychology class. So we use the central limit theorem, even though we don't go into a proof or anything like that. But rather we just kind of use the implications of the central limit theorem. Here's what the central limit theorem says. Okay, if mu is known, okay, remember that mu is the population mean. Okay, or if we can assume what mu is, we can have a logical value for what the population mean should be. The central limit theorem tells us that taking all possible samples, every possible random sample that you could come up with or think of, right? And this is why it's theoretical, we don't actually do that. But if we could take, okay, imagine in your mind, if we could take all possible random samples of a particular size n, and we take the mean and we put it in a pile, that is going to produce a normal distribution of means when the population standard deviation is known. Okay, this is Greek symbol sigma. It stands for population standard deviation. Okay, so what that says is that if we know the population mean and we know the population standard deviation, if we take all possible random samples of a particular size, calculate the mean, put those means in a pile, the pile of means will form a normal distribution. And that normal distribution has certain properties, in particular that the most frequently occurring mean in that pile of means will be equal to the population mean that it was sampled from, right? So that's the most probabilistic result, is that when you take multiple random samples, and not even multiple, but many, 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 many random samples of a particular size, and you put those means in a pile, the mean of those means will equal the population mean from which they were sampled. Okay, but there will be a distribution that forms. Not every mean will be exactly equal to mu. Some will be a little bit more, some will be a little bit less. Okay, so that height of the curve tells you what is the most frequent versus the most infrequent. Okay, so the low height of the curve tells you that it would be very infrequent to get a mean that had a value that was quite a bit less than the population mean. It would also be, it happens not frequently at all, to get a sample mean that has a value that is much, 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 much higher than the population mean. Okay? So another way of saying that too is that what is most probabilistic to happen is that we would sample a sample mean that is close to the population mean, and it is less probable to sample a sample mean that has a very high value or a very low value. Now, what you see overlaid here too is this dashed line. This is a t-distribution. Recall that we're doing a one-sample t-test. We have to do a one-sample t-test when we don't know what the population standard deviation is. That is when sigma is unknown. And we end up estimating sigma from our sample data. Now, for reasons that I'm definitely not going to go to into this tutorial, the resulting distribution under those circumstances looks very similar to a normal distribution, but it's just a little bit different, and so it's called a t-distribution. Okay, so it's a bell-shaped curve. The most probabilistic thing to happen is that you would sample a mean that is close to the population mean. It's less likely to get sample means that are either much, much lower or much, much higher. And we have this bell-shaped distribution. But it just turns out that the tails, and that's what the ends of a distribution are called, the tails of a distribution. The tails in a t-distribution are just a little bit thicker. All right. So why do we care about a sampling distribution of means? Why do we care about a normal distribution of means? Or why do we care about a t-distribution of means? Oh, sorry, I want to tell you just a little bit more about t-distributions. It turns out that there's actually many t-distributions. While there is only one standard normal distribution, there are actually many different t-distributions, and the exact shape of the t-distribution depends on a concept known as degrees of freedom, or DF. Degrees of freedom is very simply calculated as sample size minus 1. And so basically what this says is the t-distribution that is formed by this random sampling process will take on slightly different shapes depending on if we're generating all of these many, many samples based on a smaller sample size or a larger sample size. Okay. But ultimately, at the end of the day, all the t-distribution is a big old pile of means that is formed by taking all of these random samples from a population with a known mean. Okay, and so this resulting t-distribution will have its mean of means in the t-distribution, and we'll also have a standard deviation. And this is just to say we can calculate all this stuff. So the central limit theorem tells us that the mean of means is equal to the population mean, and that the standard deviation of this distribution of means can be calculated. There's a bunch of formulas. This is a big headache, but you get it in stats class. But for the point of this tutorial, we'll just say it can be calculated by coming up with an estimate of population variance. And that's important because what this standard deviation of the distribution of means tells us is, kind of roughly on average, when we do this random sampling process, we expect that any sample mean that we could sample, our best guess is that it will equal the population mean, but we know that it will be, different by some amount of error. And so that one standard deviation tells us about how much of a difference is reasonable to expect just by chance alone. Like, what would be an amount of difference that we could see between a sample mean and the expected, basically population mean that could happen just due to this random sampling process. So that's what this standard deviation of this distribution of means tells us. And so that actually has a special name in statistics. And that's called the standard error of the mean. That standard error of the mean tells us about how much we can expect any sample mean to be in error as an estimate of the population mean. Another way of thinking about that is for any possible sample mean that we sample, we expect that it will differ from the population mean, and that standard error will tell us by about how much. Now, in doing null hypothesis significance testing, what we're going to do is we're going to use the properties of these sampling distributions, in this case the t-distribution, to establish values of the sample mean that are unlikely to be sampled. Okay? Remember that that's what null hypothesis significance testing is all about, is we're going to establish a t-distribution that is based on sampling from a population in which the null hypothesis is true. So let's think about our example of lottery winners and whether winning the lottery increases happiness. If we start with the null hypothesis that winning the lottery doesn't increase happiness, right? Well, then we have to say, like, well, so what is the case in the population if the lottery doesn't increase happiness? Well, that's just like normal. Like if we knew what kind of normal, or let's just say typical, that might be the better word. If we knew what typical or kind of average happiness levels were in the population, that's our starting place under the null. Okay, well, we have data on that, right? So in fact, to measure happiness, one kind of standard question is to literally say, on a scale from 0 to 10, where 0 is your worst possible life and 10 is your best possible life, actually is conceptualized as a ladder, where 0 is the lowest rung on the ladder and 10 is the highest rung on the ladder. What rung on the ladder is your life? Pick a rung. And so it's literally a 0 to 10, right? So if we know in the United States that the average happiness is like an 8 on that, and I think that's close. This has been studied quite a bit, okay? And let's just use that as our starting place. If we know that the population mean is 8, so mu is 8, and then we're going to say, all right, well, I want to do a study that has lottery winners in it, and I want to compare whether they have a higher mean than average. What you first have to do is say, well, what would happen if we just randomly sampled from the population in general? And if we took every random sample of 16, like what are the means that we're likely to get? Okay, so let's just take 16 random people, calculate their mean, and then let's do that random sampling process over and over again. So we're going to get some sample means that are right around that population mean of 8. Some are going to be a little bit more, some are going to be a little bit less. But what we're interested in are those means that are so far away from 8 that those means happen less than 5% of the time. And that'll be our basis for establishing, well, if our lottery winners get a mean that is past that threshold, then we're going to say that that's a statistically significant result, because a sample mean that is that far away from the mean of 8 happens less than 5% of the time in our sampling distribution. Okay. So that t-distribution or a sampling distribution allows us to say what is the value that we need for a sample mean in order to be considered basically rare, okay, or improbable, assuming first that the study doesn't work or the effect doesn't work and the null is true, okay. So what we can do is we're going to, you'll see this line here. This line is associated with a critical value, and so once that mean value is converted to our t-statistic, that will give us a number that we can say, past that number, those means are just too large. They're improbable. They happen less than 5% of the time, based on just sampling from our kind of untreated comparison population of just regular old people with a regular happiness score. Okay, so the way that we do the t-test for a single sample, or that one sample t-test, is we're going to take, here's our formula. We're going to take our sample mean. So in this case, in our research study, I'll just continue the example. We'll take a sample mean from our lottery winners, and then we're going to look at the difference between the mean for our lottery winners versus the population mean in the untreated population. So these would just be regular people, let's just say in the US, that don't win the lottery, and we know, because we have this data, what the average happiness score is. The standard error of the mean, that goes back to that sampling distribution. Okay, it's the standard deviation of that sampling distribution, but ultimately this is the amount that we expect any sample mean to be an error as an estimate of mu. Or another way of phrasing it is, for any sample mean that we just randomly sample about how much do we expect it to differ from the population mean. So what our t does is it looks at the actual difference that we got between our sample mean and the population mean relative to how much of a difference we expected just due to randomness. So what you can see is that when the t statistic starts getting large, or we're observing much more of a difference than we expected due to randomness. When the t is small, we're expecting like about as much of a difference as we would expect just due to randomness. And when I say randomness, I'm just talking about this, right? Like via a random sampling process, we get all kinds of different means, and some means have a high value and some means have a low value, and that just happens randomly, right? So our standard error captures about like what would be like a typical amount of randomness, if you will, right? And so if our actual difference is very large relative to like a typical amount of say error or randomness, then we have a large t statistic, falls in our critical region, and that is when we have statistical significance. Okay. Now what we do is with our region of significance, we come up with a critical value of t that becomes our threshold. Okay. So when we say we're going to calculate our t statistic that evaluates the difference between our sample mean, population mean over standard error, ahead of time, we come up with a value of t that we need to basically surpass. Okay, and that's our critical value of t. So that's based on the number of people in our study, or n-1 degrees of freedom. In this case, we've got, let's just say we had our 16 lottery winners. This is obviously an abbreviated table, but we've got 16 lottery winners that are going to be in our study. So 16 minus 1 is 15, so 15 degrees of freedom. You'll notice that we've got different choices for statistical significance levels. In psychology, as well as other social behavioral sciences, the conventional level is 0.05. So if we do a one-tailed test, and I will explain the difference between a one-tailed test and a two-tailed test in just a minute, what this table tells us is that our critical value of t that we're looking for, that will basically separate the top of the sampling distribution from the rest of the sampling distribution, is 1.753. What that means is that when we actually calculate our t statistic based on the results of our study, we're going to be looking for a sample mean that when is converted to a t is going to be larger than 1.753. All right. So I said I was going to explain, so you'll notice that we've got these one-tailed tests and two-tailed tests. So one-tailed tests and two-tailed tests are associated with directional versus non-directional hypotheses. So directional hypotheses specify a direction of the effect, as in money increases happiness. That's a prediction. I predict that winning the lottery or getting money, that will increase one's happiness. Alternatively, a drug would reduce the number of hallucinations that schizophrenics have. Okay, so there's a clear prediction about the direction of the effect. There's either an increase or a decrease that is predicted. Directional hypotheses use one-tailed tests. So if there's a predicted increase, like that's what the hypothesis does, it predicts an increase, you're interested in the upper tail of the t distribution. If you have a predicted decrease, as in the drug reduces hallucinations, you're interested in the lower tail of the t distribution. Okay, so these are our t distributions, right? This is what would happen. We assume the null is true. We start from a place, all right, population average happiness is 8. Let's take all possible random samples. Let's get a distribution of means. Here's our pile of means. When converted to t statistic, here's a critical value that I'm looking for, 1.75, but I'm only interested in that upper tail of the distribution if I think that money is going to increase happiness, right? Like we're centered around the population mean of 8, so I'm really only interested in an increase, one-tailed test. Similarly, here's a lower tail of the distribution, so if I'm looking for a reduction, okay, like the drug reduces the amount of hallucinations, whatever the average amount of hallucinations is, I'll be looking for a number that is lower than that. We can contrast that with non-directional hypotheses. So a non-directional hypothesis does not specify a direction of the effect. So for instance, we might just have the prediction money has an effect on happiness. I think that lottery winners are going to feel differently in some way than the average person. Maybe they'll be more happy, but maybe they'll actually be less happy because with all the money, it's a new lifestyle, it's a whole new set of problems. It brings stress. A bunch of people looking for handouts, right? So people that win the lottery, and in fact, that's actually true. That's an established research finding that people that win the lottery are no more happy than kind of the average person. So initially, there's kind of a spike in happiness, but then people kind of return to whatever their baseline levels were. Okay. Anyway, sorry, getting into the psychology here, but we have a non-directional hypothesis because we're saying, well, it's going to be one or the other. So I'm interested in, I'm interested in a study result that would show either an increase or a decrease. Let's take another example. Negative feedback has an effect on job performance. Notice the researcher isn't saying one way or the other. Maybe, negative feedback, you point out all the things that the employee is doing wrong, and they're like, oh, cool, I was doing all those things wrong. I'm going to stop doing those things wrong, and so their job performance gets better. So we see an increase in job performance as a function of the negative feedback. Alternatively, maybe it's the case that on average, that this negative feedback doesn't really work, because if all you're pointing out are all the things that the person's doing wrong, could be demotivating, and people are like, oh, this sucks working here. I'm not gonna try nearly as hard. So it's kind of an open question, is to say, well, what is the effect of giving negative feedback? On the one hand, I could see that it could have a positive effect, increase job performance. On the other hand, it could have a negative effect and it could hurt job performance. So I'll be interested in looking for either an increase or a decrease. Okay? So in either case, if there's a non-directional hypothesis, in looking for either an increase or a decrease, we'll look for both tails of the distribution. Okay, and that's when we do a two-tail test, because we'd be interested in a sample mean that is unlikely to be randomly sampled from that kind of comparison distribution or the null distribution. And we'd be interested in either sample means that were very high or very low, in terms of stuff that would just happen randomly. Now notice what a two-tail test does to your critical value of t. It increases it. And the reason is because we still keep the same level of significance, this 0.05, okay, we're still interested in sample results that happen less than 5% of the time, assuming that the null is true. But what we have to do is in our probability distribution, we have to split that 5% up. We have to split that 5% from a single tail into both tails. And so what we're doing is we're now moving our critical region further out into the distribution. And so now we're interested in the top 2.5% of our distribution and the bottom 2.5% of our distribution. And that will be associated with t-values that are kind of further out, or they're more extreme. The way to interpret a t-value is it's literally the number of standard errors that your mean is away from the mean of the means. So what we're saying is, in the first case, is that we'll be looking for a sample mean that is more than 1.753 standard errors away from the mean. Here we're saying we need to have a sample mean that is more than 2.132 standard errors away from the mean in either direction. So you notice that there's only positive numbers here. That's because a t-distribution is symmetrical, but we are interested in a critical value that is positive 2.132 or negative 2.132. All right. And then finally, we can calculate an effect size for the t-test. The way that we do this is that we've got a general formula, which is that an effect size, this is Cohen's d, Cohen is the person who came up with this statistic, is calculated as the mean in the population of the treated population versus the mean for the untreated population. So looking at the mean difference. So we could say these would be our population of lottery winners, and these would be the population of regular folks that don't win the lottery. So we're looking at the difference between those two divided by the standard deviation in the population. So notice that this is kind of similar to the t-statistic, but the main difference is that we're not using standard error being about a sample mean, but rather we're just talking about what the standard deviation is in the population, which is kind of the average difference in the scores among people. All right, so this is the general formula, but we of course don't know what the population mean in our treated population is, so we use our sample mean as an estimate of the mean of our treated population. Okay, mu2 would be the mean of our untreated population, and then sigma is the standard deviation of the population, which is estimated using our sample standard deviation. And then these are some conventions for interpreting whether we've got a small, medium, or large effect size. So, all right, that was pretty much a crash course in doing a one sample t-test, but that reviews some of the elements of null hypothesis, significance testing. Hope you found that useful and have a better handle on kind of conceptually what a one sample t-test is and what it does. Thanks for watching.